signals g1 of t is equal to 1000 brick 4000 t and g2 of t 2000 triangular 8000 t are applied at the inputs of ideal low pass filters h1 of f, that is equal to brick f over 8000 and h2 of f brick f over 5000. The outputs y1 of t and y2 of t of these filters are multiplied to obtain the signal y of t is equal to y1 of t, y2 of t, and find the Nyquist rate y1 of t, y2 of t, and y of t. Use the convolution property and the width property of convolution to determine the bandwidth of y1 of t and y2 of t. Okay, now let's go ahead and see. So initially we have g1 of t, g2 of t, and that one goes through these given low pass filters, and then we are deriving y1 of t and y2 of t. First let's look at y1 of t and y2 of t, how it's gonna look like. So let's take the y1 of t first. Initially we have g1 of t. Initially we have g1 of t and that is given by the formula 1000 brick 4000 t. Okay, now in order to find the bandwidth we had to convert this one into frequency domain, so we had to do the Fourier transform. If you do the Fourier transform of this one, that is, you can use this property. One of the properties says that if you have a brick t by tau in the time domain, in the frequency domain, that is equal to, if you take the Fourier transform, that is in the frequency domain, tau sinc phi f tau. Okay, so from this one you can see it's you can analyze the pattern. Here currently we have phi, and so assume the amplitude is 1, and then phi multiplied by t over tau. In this case the tau is 1 over 4000, because if you put 1 over 4000 in the denominator you will get 4000 t. So since tau is 1 over 4000, then if we multiply this one by that, so we are going to end up, so let's put this equation first. 1000 phi 4000 t, and I'm taking the Fourier transform. That's going to be 1 over 4000 multiplied by 1000, that is 1 over 4, and then sinc, and then phi f tau. Okay, phi f remains the same, and instead of tau we are going to multiply this one with 1 over 4000, so we are going to have 4000 in the denominator right here. So this is the conversion for the first one given. Okay, now let's look at the second one as well. In the second one we have g2 of t that is given, that is g2 of t, that is 2000 delta 8000 b 8000 t. Okay, and the Fourier transform of this one also similar to what we have for the this rectangular. Okay, the only difference is now it's going to be double, so when you multiply this one by this, it's going to be double the whatever we have. Okay, so if it says 1000, then we are gonna double the multiplication, like 1 over 16,000, and then if it's 8000, we are gonna divide this one by double of that, that is 16,000. So that's the only difference for triangular and the rectangular. So the Fourier transform, if we take it 2000 triangular, 8000t, and the Fourier transform of that one will come like 2000 divided by 16,000, that's gonna be 1 over 8,000. 2000 divided by 16,000, that's 1 over 8, and then sin square, and we have t right here. Okay, sin square, then we are going to have 5f, that one divided by 16,000, the double of it. Okay, you see it's almost similar, but the thing is now we have double. Okay, and this one, you know, this one is a brick that looks like a 5, but this is brick, and the triangular almost the same, but this one for the triangular it's doubles, like the division doubles, so it's like you are multiplying by 1 over 16,000, and here you are multiplying by 1 over 16,000 as well in the front. Okay, and that is it. That's a conversion. Now we have here, we have sinc, and this is sin square. So from this one we can right away see the bandwidth is for the first one is 4000. Okay, let's write this one down. So bandwidth for the this is for the g1 of this is equal to g1 of f. This is g1 of t, so this one is g1 of f, and this one is g2 of f. Okay, and also we had to consider before we pass through the bypass filter, the bandwidth for the g1 of f is 4000, the bandwidth for the g2 of f is 16,000, but after this pass through the low pass filter is going to change. Now let's see how it's going to change. So the low pass filter h1 of f is given by a brick f over 8000. Okay, now if you want to see illustration, after the conversion of this thing, we are going to have a graph like this. Okay, we are going to have a graph for this one. I'm drawing for this one, that is g1 of f. So we have a sinc graph. The sinc graph look like this. It's like a wave pattern. Like this. Okay, in this case this is minus 8000 and this one is plus 8000. And what's going to happen is now we are sending this h1 of f through this. H1 of f is a brick shaped, and this one has a height of 1 over 4. Okay, and the h1 of f, this is g1 of f. Now if I draw the diagram for h1 of f, That's going to be just a brick with bandwidth of 4000 each side. So starting from negative 4000 to 4000, and it has a height of 1. So if you pass this one through this, anything external is going to be removed. Like if you have any value extra after 4000 is going to be removed. If you have any value after anything above 1, it's going to be removed. But in this case the height is only 1/4, so that's going to remain, and whatever the value inside of this 4000 is going to be included, others are going to be eliminated. Now let's see that. So what you're going to end up having is, in the sync wave we're going to have a shape after passing through the low pass filter. You're going to have shape that is negative 4000, that's like this, and then positive 4000, and the height will be included whatever the value below 1, but in this case this is just 1/4 the height is, so it's going to be included. So from this one, for the bandwidth of G1 of t, and this one is Y1 of f, okay, this one after passing through the low pass filter it becomes Y1 of t, but in the frequency domain that's Y1 of f. So this is the frequency domain, and then bandwidth of Y1 of f is just 4000, but here they also requested the Nyquist rate. Nyquist rate is basically the double of whatever we have, so we can say Fn, that's a Nyquist one, that is 8000 Hertz. If the bandwidth is 4000 Hertz, Nyquist is double of that, that is 8000 Hertz. And for Y2 of t, similar thing happen. If I draw the graph, let me use a different page for it. So for Y2 of t, what we have 1/8 sin square this is G2 of f, okay. G2 of f is equal to 1/8 sin square phi f over 16,000. Now let's go ahead and draw the diagram for this. So sin square is almost similar to the sync diagram, but it's gonna have this upper part only, like this. Okay, and it has a height of 1/8, and this one is negative 16,000, 16,000. Now what we are doing is we are sending a low pass filter that is with again a brick with 5000 total bandwidth. Let's write the equation first, that is brick f over 5000 so that shape is gonna look like this. Negative 2500, 2500. So if you send this one through this, and also this one has a height of 1, so what happens is whatever the value below this 1 is going to remain. So here 1/8, that's going to remain. And then 2500 is going to cut everything after 2500. So we are going to end up having a shape that is similar to this. Okay. This one is for H1 of H2 of F, and this frequency. And then if we draw the diagram for, and this one is G2 of F, frequency. Now we are drawing Y2 of F, that's after going through the low pass filter. Here what's happened is, let's say this is where it's meeting at negative 2500, so it's gonna cut off right there, and then there, and that's it. It's gonna have that much only, and whatever the value below 1, and in this case this is the height is just 1/8, so it's gonna remain like this. So the bandwidth of Y2 of F is just 2500 Hertz, but the Nyquist is going to be double of that, so that's going to be 5000 Hertz. Okay, and now we have done the Y1 of t, Y2 of t. Lastly we have to do Y of t. Let's do that. Y of t is equal to Y1 of t multiplied by Y2 of t. Okay, but in the frequency domain, this is in the time domain. In the frequency domain, that's going to be just the addition. So y of f is going to be convolution of y1 of t with y1 of f with y2 of f in the frequency domain. When you multiply in time domain, that's convoluted in the frequency domain. So that's going to be just going to be end up as an addition in the frequency domain. So we are going to have bandwidth of y of f as adding these two, that is 2500 and then 2500 and then 4000. That's gonna be 6500 Hertz, and that is normal bandwidth. But if you take the Nyquist, that's gonna be doubling. That's gonna double, so that is 13,000 Hertz. Okay, and those are the required thing. We had to find out y1 of t and the bandwidth of it, y2 of t bandwidth, and then Nyquist rate. That is, if you find the bandwidth, Nyquist rate is just the double of it, and then y of t. So we have to first convert all of them in the frequency domain to find the bandwidth, and the Nyquist rate is basically double of whatever the bandwidth we derive. Okay, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.